Hey, welcome back. Today we're going to be talking about what are Kepler's laws, what are related ideas, and how can you derive the third law for AP Physics E Mechanics. So we're talking about all the related ideas related to Kepler's laws. And I'm going to teach this in the context of a forces unit because that's primarily where this comes up. I'm also going to introduce some later ideas that relate to it. So let's go ahead and get to it. First of all, orbital velocity to the moon. So this is something that you're going to need to know how to do. And if you have something moving in a circular path, the question is, how fast is it going? And so one way to reason through this is to talk about the sum of the forces. So in this case, we don't really have an X or a Y axis that we want to work with. Sometimes I usually say F in for the subscripts here. But what's pulling it in for this system right here, if you're talking about a circular path, like say with the Earth and the Moon, that's going to be the force due to gravity, right? And we already know about Newton's universal law of gravitation. That's going to be going right in here. The second line for something moving in a circular path is we're going to write F equals ma. But here, we're going to modify the a because this is moving in a circular path, and we know something about centripetal acceleration as well. We can set these two equal to each other and sub in for centripetal acceleration what we already know about it. We know that is vt squared over r. So that's what we're going to go about doing. Let's write this out, and this is our tangential speed over here. We can think about what m1 and m2 are and compare that with this m over here. If you think about it, this is the object that's going around in a circular path. We could call that the mass of the orbiting object, so mu, so to speak. And then this is the mass of the orbiting object, the mass of the center object, you could say. So it's the mass of the orbiting object that's going to get canceled out here. So we can take a look at what I'm talking about here. This one gets canceled out, this one gets canceled out over here. And this is something you're going to need to know how to do quickly on a test. It's pretty easy to do once you're familiar with it and have had some practice. You can also cancel out one of the r's on the left and the r on the right and solve for the speed at which this object is going around in a circular path. And that's what we're attempting to do here. So that's what we mean by the orbital velocity of the moon treated as a circular orbit. Something that is related to what we're talking about here that you are expected to know how to do. Alright, let's continue and talk about some other related ideas. So, what an ellipse is, this right here is optional material in here. You don't need to know all of this. But what is an ellipse? What is an ellipse? Well, it's something that if we set up our definitions for A, B, and C here, I'm not going to read all of them at you. But if you take a look at what our A, B, and C are here, that if you add them up together, that R1 plus R2 is equal to 2 times A. So that's going to be our major axis. So in other words, this length plus this length is going to be equal to this length over here. If that's the case, then we're talking about an ellipse. And planets are going to be traveling in an ellipse around their stars. And so it's important to know kind of what an ellipse is. The eccentricity has to do with how oval the ellipse is, so to speak. So it's just a ratio of the C over A values. Alright, so that's a little bit of extra info just to understand what we're talking about when we're talking about an ellipse. And next up we have analyzing the motion of a satellite in an elliptical orbit. So if you take a look over here, you've got, let's say, a center planet right here and a satellite that's going around the planet like this in an ellipse. And it's important to think about, alright, notice that the farther away the satellite is, the slower it's going to be going, and the closer it gets, the faster it's going to be moving in terms of its tangential speed here that you see for like this V1 or the V2. Now, we can say a little more about this. We can say the initial angular momentum, so like at point 1, is equal to the angular momentum at point 2. At this point in your training, you may not have gotten to what angular momentum is. There's a lot to say about that, but just know that we can break this down. The way that I like to think about it is to think about someone doing a hammer throw. If you think about a hammer throw, as the hammer is spinning around, there's quite a lot of momentum. With the hammer as it's going around, you can describe it in different ways. So this omega, this W looking thing right here, is talking about what the rotation is in terms of radians per second. So the motion of the hammer throw guy as he spins around would be like omega 1, you could say. And this I value, this is called moment of inertia or rotational inertia. Again, we'll talk about it later in the course, but that's going to give you the idea that it matters how mass is distributed. So if most of the mass is distributed towards the outside here, that is different than if most of the mass was distributed really close to the handle for the hammer throw guy. So that's just conceptually how you can start thinking about these things if you are in a forces unit right now and you haven't learned about angular momentum yet. But it turns out that angular momentum is conserved. That means the total amount before an event is equal to the total amount after an event. So if we take that to be true, we can sub in what we know once we have learned about moment of inertia. For point masses, we've got that for this point mass 1 and point mass 2 over here. And if that's the case, then we can continue. Now, this is a very important equation because it's going to relate linear motion on this side of the equation with angular motion on this side of the equation with the omega. So this is a small but mighty equation. And what we can do with that is we can isolate for the omega and then sub these in for omega 1 and omega 2. And if you do that, then what happens is you get something like this. Now notice that we've got r squared and one of the r's over here, and r2 squared and an r2 down below here. So we can cancel out one of those r values out of the squared function, and you can end up with this. This is a really very small but very important equation. I highly recommend that you do memorize this equation. It's not on your equation sheet, but it's something that you should be aware of. Meaning if you take a look at this r value multiplied by this v value, that is equal to this r value over here, this r2 times v2 over here. Really easy and useful way of dealing with givens on an FRQ. Alright, let's continue and talk about Kepler's first law. So Kepler's first law is the idea that the orbit of a planet is an ellipse with the sun at one of the two foci. Alright, very good. That's easy enough, right? That's all it is. That's Kepler's first law. Let's talk about Kepler's second law. Kepler's second law is the idea that a radius vector joining any planet to the sun sweeps out equal areas and equal lengths of time. This is pretty amazing. In other words, if you take a look at the blue area that's being swept out here, and if you were to calculate that area, the area would be the same the entire way through. So the green arrow represents the velocity, purple arrow directed towards the sun is the acceleration, or you could say the force. The other two purple arrows are acceleration components parallel and perpendicular to the velocity. That blue area is going to be the same all the way through. So that's a visual representation of Kepler's second law. Alright, and Kepler's third law. Let's start with our basic definition of average speed or average velocity. And so this is it. And if we assume that we've got one revolution for the distance traveled, and the time we will call a period, then if we do that, then we can rewrite this, because this now is going to be the one revolution. You could say circumference is equal to pi times diameter. This is just another way of writing that. And then for the time, we're going to call the time for one complete cycle a period. That's an important concept. If you're still in your forces unit for AP Physics C Mechanics, it's important to recognize that this will call capital T, and that will represent period, time for one complete cycle. Alright, next up, recall towards the end of our previous work with the sum of the forces, just Fg, and setting that equal to MAC, we ended up with a V squared value. So, this is what we had come up with previously. We said V squared is equal to this. Well, what if we squared both of these and then subbed this in? What would happen? So, let's think about what would happen here. What we're going to do is we subbed this in for v squared. So we squared this part of this side of the equation, and then we're going to square this side of the equation and think about what happens next. So we continue to simplify. If you take a look at what's going on here, this is now 4 pi squared r naught squared, and this is going to be the period squared. And if we continue to simplify, we end up with period squared is equal to this. And this is Kepler's third law. So this is an important way to derive Kepler's third law. It's something you should be aware of for AP Physics C mechanics, and you should be able to solve problems with it. I do want to say I've done screencasts on an entire year of physics at this point, and most of the ideas for AP Physics C mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.